All right, good morning. This is the first of 3 videos on exponential growth and decay, section 3.8. After this, there's a couple more videos on related rates problems, that's section 3.9. So both of these sections are pretty dense, and it's all word problems, so they take longer. And so today's class was supposed to be a fairly difficult class, and classes got canceled, and I don't want you to get behind because we want to have a week to study for our final exam at the end of the semester. And if we just skipped class today, we wouldn't have that time. So, but the nice thing about having videos to watch is you can pause, you can rewind, you can watch them over and over while you're doing your homework. So yes, you have web-assigned homework to do over the spring break, and you should be doing that homework, do a little bit every day because it's going to take a while. The assignments might not look long, but they do take a long time. But these videos should help you. Okay, let's get started. Exponential growth and decay. So first, suppose a quantity y is increasing or decreasing at a rate that's proportional to its size at any time t. What does that mean? Well, the rate is dy dt, and proportional to its size, well, the size is y. So that means that dy dt has to be equal to k times y for some non-zero constant k. And this is sometimes called the law of natural growth. A quantity that satisfies this equation is said to obey the law of natural growth. And this equation is called a differential equation, which we've seen a little bit before. And I just want to remind you, a differential equation is just an equation that involves an unknown function. So y is the unknown function, and it also involves the derivatives, at least one of the derivatives of y. So solving a differential equation means figuring out what the function has to be that satisfies the equation. So, first of all, one particular solution to this equation is the function y of t equals c times e to the kt, where c is some other constant and k is the same k that's in the differential equation. So, how do we know this is a solution? Well, we can prove it's a solution by plugging it into the equation. So we're going to plug y in. We're going to plug in c e to the kt for y. And we also need its derivative. So let's find y prime. Y prime is going to be c e to the kt times the derivative of kt. So y prime is c e to the kt times k. And, well, that's just k times y. So it's quite obvious that it does satisfy that differential equation. And so what about that constant c? Well, we can find that constant c just by plugging in t equals 0. So if we plug in t equals 0, we get y of 0 is equal to c e to the k times 0. And that's just c. So now we know that a solution to the differential equation is y of t equals y of 0 times e to the kt for some constant k. Well, it turns out that this is the only solution. So this is a theorem. We're not going to prove this theorem, but it says that the only solutions to the differential equation dy dt equals k times y are these exponential functions. Y equals y of 0 times e to the kt. So this is the theorem we're going to be using throughout this section. If we're told that some quantity obeys the law of natural growth, then we know it satisfies that differential equation, dy dt equals ky. And if we know that it satisfies that differential equation, then we know exactly what it looks like. We know it has to be an exponential function of the form y equals y of 0 times e to the kt. So that's what we're going to use in all of our problems in this section. So, one of the most natural applications of the law of natural growth is population growth. So if P is population, and we know that dP dt is equal to Kp, and that's because we know that population obeys the law of natural growth, so it has to satisfy that differential equation. Well, we can divide both sides of this equation by P. So we get K by itself. And so it's equivalent to this equation. K is equal to dP dt over P. Well, this latter equation, this K, written this way as dP dt over P, this is the growth rate divided by the quantity. And both of these are functions, right? The growth rate, dP dt, is a function of t. The denominator, p, is also a function of t. But the ratio is a constant, k. And so this k is called the relative growth rate of the function p. Okay, so it's a constant. The relative growth rate is a constant. If p is a function that satisfies the differential equation dP dt equals kp, then we know the relative growth rate of that function is a constant. So, in words, what do these two equations say? The first one says the growth rate at time t is proportional to the population at time t. So, if you're given a problem and you see that it says the growth rate at time t is proportional to the population at time t, well, you know that's equivalent to saying that the relative growth rate of that population is a constant. Okay, so these are equivalent statements, and we're going to be doing problems in which we're given one or the other of these statements. So let's start out with problem 1. So hopefully you printed out that handout. If not, you should pause right now and print out the handout or write this problem down. So it says a population of protozoa develops with a constant relative growth rate of 0.7944 per member per day. On day 0, the population consists of 2 members. And we're asked to find the population size after 6 days. So we can see we're given that it has a constant relative growth rate. So that means that dP dt over P is constant. It's 0.7944. And that means that dP dt is equal to that constant times P. because it has to satisfy that differential equation. If it has a constant relative growth rate, then it satisfies that differential equation. And if it satisfies the differential equation, then we know exactly what the solution looks like. We know P of t has to be P of 0 times e to the kt, where k is 0.7944. And we're also given the initial population. So we can substitute 2 for P of 0 and say that P of t is equal to 2 times e to the 0.7944 t. Okay, so now all we have to do is find the population after 6 days. So we plug in 6. P of 6 is going to be 2 times e to the 0.7944 times 6. And putting that into our calculators, we get approximately 235. So remember, whenever you're dealing with living organisms or objects that can't be chopped up, you should also round to the nearest whole number and probably round down, because you can't have a piece of a person or a protozoa or a bacteria cell. Okay, so last week we saw an example of natural growth, law of natural growth. So last week we saw this example. We had a bacteria culture. It started with 500 cells, and we were told that it doubled in size every hour. So we found the population function to be P of t equals 500 times 2 to the t. And we did this just by plugging in a few times and looking for a pattern. And so this doesn't have an e in it. It has base 2. But let's explore it a little further. We found that the derivative dp dt was 500 times 2 to the t times the natural log of 2. Well, this looks like k times p, right? P is 500 times 2 to the t, and so k would be natural log of 2. So that was the rate of growth when we did that example. So what is the relative growth rate? Well, it looks like it should be natural log of 2, but let's just write it down. So k has to be dp dt divided by p, and dp dt was 500 2 to the t times natural log of 2, and p is 500 times 2 to the t, and yes, it does turn out to be natural log of 2. So this population, 500 times 2 to the t, is a function that satisfies the law of natural growth. So that means that we should be able to write it. So another way to write the same function is P of t equals 500 e to the kt, and k is natural log of 2. So are these two things the same? 500 times 2 to the t and 500 times e to the natural log of 2 times t. Well, we can rewrite e to the natural log of 2 times t as e to the natural log of 2 raised to the t using laws of exponents. And we know that e to the natural log of 2 is just 2. So we do have 500 times 2 to the t. So this is just two different ways to write the same function. 500 times 2 to the t is the same as 500 times e raised to the natural log of 2 times t. Okay, so that's that example, or those two examples, and that concludes this video. The next video we'll do another example. We'll talk about exponential decay.